Okay, I'm back. 11.6, last section on series tests. Today we're going to talk about absolute convergence and the ratio and the root test. So this is going to be a little bit longer, so brace yourself. A series is called absolutely convergent if, well, regardless how this looks, if we take the absolute value of every term and we look how this behaves, so if the absolute values of the sequence term, when we put that into a series, and if that series converges, then the original series is called absolutely convergent. Oh, shoot. So absolutely convergent. There we go. So theorem, and this is the big one. If a series is absolutely convergent, it's also convergent. The proof of this is page 738 in your text. Again, I'm not going through all the details of the proofs. You guys can look them up online. You're welcome to read them in your textbook, and if anybody wants to have a conversation about it, I'd be more than happy to. So what we want to do, sometimes it's easier to show that a series is absolutely convergent. So if a series is absolutely convergent, then it must be convergent. No, it's not necessarily the other way. A convergent series isn't always absolutely convergent. So be really careful. We can only go in this direction. But if we can show a test is absolutely convergent, we can show it's convergent, but it does not necessarily go in the other direction. So let's just write that down. Excuse me. Allergies. I don't have the Rona. Let's see, not that I know of anyway. But a convergent series is not necessarily absolutely convergent. A series may be convergent and absolutely convergent, but just because it converges, it doesn't mean it's absolutely convergent. If a series is convergent, but it's not absolutely convergent, we call it conditionally convergent. So for example, previously we have showed, or we just showed in the alternating series section, that the alternating harmonic series, -1 to the n minus 1, 1 over n, is convergent. The alternating, and you can always use this as a fact for all future tests. So the alternating harmonic series is convergent. You can use that as a fact, put it in your notes. But if we take the absolute value of the terms, n equals 1 to infinity, the absolute value of -1 to the n minus 1, 1 over n, that's going to make this all the terms positive or just 1 over n. And this is divergent. And we've shown this in previous lectures also. So this is the harmonic series, and the harmonic series is always divergent. So by alternating the terms positive and negative of the harmonic series, we create a convergent series. The sum would be finite. If we keep them positive, then it will add up to infinity. It's divergent. So here's an example of a series that's convergent, but its absolute value is not convergent. So therefore we say the alternating harmonic series, -1 to the n minus 1 times 1 over n, is conditionally convergent. N equals 1 to infinity. So given a convergent series, if its absolute value also converges, it's called absolutely convergent. If we have a convergent series, but its absolute value of that series doesn't converge, it diverges, we call it conditionally convergent. So we like when something's absolutely convergent. So absolutely convergent implies the original series is convergent. That's our theorem that we are going to rely on. Absolutely convergent implies convergent. So the next two tests are going to be based on this fact. We are going to show that series that are absolute, that given two other tests, we can show that if the series is absolutely convergent, we can conclude that the series is convergent. So the first one is called the ratio test. Given a series, I say gotta be good with your limits from Calc 1, so you might need to go back into that section, and I think it's chapter 2 in your book, and review your limits. But if we have a limit, if we can create a limit of the n plus 1th term over the nth term, and we take that limit, we calculate it, and we get its value, L. One of three things that's going to happen. It's either going to be less than 1, greater than 1, or equal to 1. If this limit is less than 1, we can conclude that the original series is absolutely convergent. Thus, the original series is convergent. If this limit that we calculate is greater than 1, we can conclude that the original series diverges. If the limit equals 1, well, the test is inconclusive and we have to use another test. So this is a good test to use when we have factorials. So let's look at this guy. Hold on 1 second, write that one down. So we are going to try to determine if this is absolutely convergent by using the ratio test. Again, the ratio test is very handy when we have factorials because we can't integrate factorials. They behave very oddly. So we're going to do the n plus 1th term, and I'm not always going to write this out, but this is really important. The algebra here can be tricky. Everywhere we see n, we're going to replace it with n plus 1. So it's 2 times n plus 1, and it's going to be that whole quantity factorial all over 5n plus 1. We just replace that, and then we're going to add this one at the end. So the limit that we're going to look for, the limit is n goes to infinity. It's going to be this whole mess, 2n plus 1, all factorial, all over 5n plus 1 plus 1, all over the original terms, 2n factorial, all over 5n plus 1. I know this looks, oh, we're taking the absolute value of this. Again, the proof of these are in the book. Now, keep in mind, when we have a fraction, dividing by a fraction is the same as multiplying by its reciprocal. I'm going to include all the algebra steps here. So this is going to be, let's distribute. This is 2n plus 2 factorial. You may not distribute factorials through addition or subtraction. And then in the bottom, we have 5n plus 5 plus 1. So that's 5n plus 6 times, and I'm just going to take the reciprocal of this, 5n plus 1 all over 2n factorial. All right, and you might be thinking, how am I ever going to take this limit? Well, let's take a look at these guys right here, because there's kind of something tricky we can do with factorials, and this comes with practice. So let's look at 2n plus 2 factorial all over 2n factorial. Now 2n plus 2 factorial means we take this number 2n plus 2 and we multiply it by the integer 1 less, which would be 2n plus 1. And then it would be times 2n. And then we would continue down this way. This would be 2n minus 1. And that's all over 2n times 2n minus 1. So this would be 2n minus 1, right? And would continue that way and would continue this way. Well, notice only the first two terms in the numerator remain. And what we end up getting is 2n plus 2 times 2n plus 1. So this is going to be 2n plus 2 times 2n plus 1. And that's it. So if we have factorials in the numerator and the denominator, we can canceling them out. We can typically cancel them out, write out the first few terms of each and see the common factors and cross them out. So now we're going to take this limit is actually equal to, because n goes to infinity, of, we get 2n plus 2, 2n plus 1, all over 5n, I'm sorry, all times 5n plus 1, all over 5n plus 6. All right. Now, you don't have to do all the algebra out. Think back of your tricks of the trade when we did limits back in calculus. If you notice in the numerator, we have a 3rd degree poly. And in the denominator, we have a 1st degree poly. You don't have to multiply it all out to see that, but if we did, the leading term would be 4n squared times 5n, or 20n cubed, blah, 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 all over 5n plus 6. So anytime the degree of the numerator, you have a polynomial over a polynomial, and the degree of the numerator is greater than the degree of the denominator, this limit is infinite. So that tells us by part 2, if the limit is greater than 1, the original series diverges. So therefore, by the ratio test, this is greater than 1, the original series, 2n factorial over 5n plus 1 diverges. Woohoo! I lost my examples. There we go. All right. All right, so let's try another one. Okay, not a factorial, but there's an awful lot going on here. This would be very difficult to show that it was decreasing. I'm not quite sure what we would compare it to in comparison test. Definitely cannot integrate this guy. I don't think it would be a nightmare. So let's use the limit comparison test. So the n plus 1th term is, ready, bear with me, -2. Everywhere I see n, I'm going to put n plus 1. So it's 1 plus 3 times n plus 1. And instead of n plus 1, it's going to be n plus 1 plus 1, because everywhere I see n, I'm going to put n plus 1, all over n plus 1 squared, 5, and now I'm going to replace that n with n plus 1, and then I'll add that plus 1 on the end. So that's the n plus 1th term. So now we're going to take the limit. According to the ratio test, it says let's take the limit of this guy, -2 to the 1 plus 3 n plus 1 times n plus 1 plus 1, all over n plus 1. Oops, I gave myself not very much room here. 5 n plus 1 plus 1, all over the series. It's the terms of the series itself. Let's see, 1 plus 3n, n plus 1, all over n squared, 5n plus 1. Now, typically I skip this step. I don't put fractions in fractions. I would have immediately just wrote this one down and wrote the reciprocal next to it. So in one step, I'm going to change this division into a product. And I'll clean it up. So this is going to be -2 to the power 3n plus 1 will be 3n plus 3. So that's 3n plus 4 for that power. And this is going to be n plus 2. Right. This denominator, I'm going to leave n plus 1 squared. Often we can do it without having to work out all those details, without having to distribute everything. So n plus 1 times, now I'm going to multiply by this reciprocal, n squared, 5n plus 1, all over -2 to the 1 plus 3n times n plus 1, right? Right, now we got to look at this thing really good. All right, first thing I'm going to do here is notice that I have the same base here. Oops, so let's take this out. That's -2. Right, so it's going to be -2 when we do 3n plus 4 minus, so I'll do it up here, 3n plus 4 minus the power 1 plus 3n. Right, so my power is just negative 3. Well, that worked out, right? 3n's cancel, then we have 4 and 1. It's just going to be, nope, it's going to be positive 3. So it's just going to be negative 2 cubed on top. And then I'm going to work with these guys. I have 5n plus 1 on top and 5n on plus 2 on the bottom. So my power here minus my power down there is going to give me negative 1. So this would be a 5 down here. We have 1 extra 5 down there. And then we have, what do we have left? Whoops, I feel like I lost something. Oh, I did read that right. So, nope, I didn't. N squared, I was looking for that guy. N plus 2 all over n plus 1 squared times n plus 1. All right. So I combined the 2's in the numerator and the denominator. I combined the 5's in the numerator and the denominator. What's left is this n squared and n plus 2 on top. And we have n plus 1 squared and n plus 1 on the bottom. All right, so we know this constant is just going to be 8/3. So I can, 8/5. So I can pull that 8/5 out. And now we're just looking at the limit of this guy. N squared, n plus 2, n plus 1 squared times n plus 1. Right, this thing. Now, again, don't make this harder than it has to be. This is a 3rd degree polynomial over a 3rd degree polynomial. When the degree at the top, when you have polynomials, this only works for polynomials, or any power functions actually. When the degree at the top is the same as the degree at the bottom, the limit is the ratio of the leading coefficient. So the leading coefficient out here is 1. The leading coefficient out here is 1. So this limit actually just equals 1. So the final answer here is 8/5. And 8/5 is, what's the damage? Let's see. I think if it's greater than 1, the series diverges. So we have another divergent series. So therefore, negative 2 to the 1 plus 3n power all over n plus 1. N squared 5 to the n plus 1. Also diverges. So this is greater than 1. So we're back at the second one. All right, so that, guys, is the ratio test. All right, you ready for it? Our last test, the root test. Given a series, we take the limit. This time we take the nth root, generically the nth root of the nth term. And we look at that limit. And this is the same conclusion as the ratio test. If this limit that we create is less than 1, the series is absolutely convergent, thus convergent. If it is greater than 1, the series is divergent. If it's equal to 1, then the series, it's inconclusive. Gosh, sorry, I got my notes all in a wacky order here. All right, let's go. Let's do it. All right, so when to use which test? Well, attached to this last section, I'm going to have a handout that sort of summarizes the test, and hopefully you'll find it helpful. And then 3.7 is going to be a really, a true testament of how well you can do sequences and series, because it's all of them all put together in one section. So you have to come up with which test to use. All right, so what we're going to do here is we're going to use the ratio test. Nope, sorry, not the ratio test. We could try the ratio test. But usually when we have powers to the nth powers, we like taking the nth root because it sort of undoes itself. So we're going to let L equal the limit as n goes to infinity. So application of we're using the root test. N to the n over 3 to the 2n. I'm going to use our laws of algebra. It's going to be the nth root of n to the nth power over the nth root of 3 to the 2n power. Whoops, limit is n goes to infinity. Well, the nth root of something to the nth power, the nth root and the nth power cancels out, and this is just n. And then in the bottom, we just have 3 squared. So this is just the limit as n goes to infinity of n over 9, which is infinite, which is greater than 1. Thus, by number 2, the series is divergent. So our original series, n to the n, 3 to the 2n, n equals 1 to infinity, is divergent. All right, one more, kids. Let's check this guy out. Again, I see powers to the n, powers with n in it. So this is suggesting that maybe we could use the root test. So I'm going to see how the algebra works out here. Again, your algebra, you have to be good with your algebra in order to do this. The algebra has to be correct. N to the 1 minus 3n all over 4 to the 2n. And I'm going to split this up. The limit as n goes to infinity of the absolute value of the nth root of n to the 1 minus 3n over the nth root of 4 to the 2n. Let's see, I know how this behaves. This gets a little, this might not be as obvious. So what I'm going to do here is, the limit as n goes to infinity. My denominator is 4 squared. But the numerator, let's see, let's do it. I'm going to write it like this so you can see what's happening here. The nth power is equivalent, the nth root is equivalent to the 1 over n power. So remember, we can treat radicals like powers. It's just a power in disguise. So I have 16 down here. And then I'm going to distribute this power. I'm going to give it to this, and I'm going to give it to this. So we get n to the 1 over n, right, minus 3. So now we need to know, how does n behave as n goes to infinity? Well, as n goes to infinity, this goes to 0. So this whole power goes to negative 3. So as n goes to infinity, the numerator is going to go to negative 3. So the limit as n goes to infinity, it's going to be, I don't know. I don't think I like how I did that. I'm going to do, you know, I'm going to write, don't do that. I don't like that. I'm going to write this. This is better. I think this is more. N to the negative 3 all over 16. There we go. Let's write this, because this just means this. Yes, I like this better. And then I'm going to write the limit as n goes to infinity, 16 n cubed down here, and n to the 1 over n. All right, and you might say, well, you didn't make it that much better? Well, the denominator is going to infinity. And if you go back and check, in 11.1, we talked about the nth root of n and what the limit as n went to infinity was, and it's 1. So go back and see 11.1 lecture, because we did that. I'm pretty sure I gave you the proof of that. So this limit is actually 0. And by the third criteria, if the limit is less than 1, the original series is absolutely convergent. Thus, the series is convergent. So therefore, we conclude n equals 1 to infinity, n to the 1 minus 3n all over 4 to the 2n is absolutely convergent. Thus convergent. All right, that's it. That's our last test, kids. That's our sequences and series stuff. So to do. Read 11.6 exercises 7 to 19 odd, 25 to 37 odd. Read 11.7. There's no lecture for 11.7. It is just 11.1 through 11.6. But they don't tell you what tests to use. So this is a true testament to how good you are with this. Let's just see, what sections are these? I think it's the same. Oh, sugars. I think it's, no, I wrote it down somewhere. Yep, 5 points. So this is 5.6 and XYZ. 5.6 homework. All right, everybody, have a great day, and I will catch up with you in our next chapter. Woohoo!